Every time you delete a file, sends a message, and runs a calculation, your computer is releasing heat. But all of us think that heat comes from things like bad engineering, such as resistance in wires and inefficient chips. But that's not the case. Not for some heat. Some of that heat is mandatory and the universe requires it. The thing is, there's a minimum amount of energy that must be released for every single information that has been deleted. No exceptions, no workarounds, and this law applies for everything from classical computer to quantum computers and even your brain. In 1961, Rolf Landauer showed that some heat is not an engineering problem at all. It's mandatory and it's demanded by laws of physics. The source of this mandatory heat is not material, it's logic. The thing is, there's a difference between logically reversible and logically irreversible operations, and the distinction changes everything. Take a look at the NOT gate, and that is reversible. If it's 0, then the input used to be 1, and if it's 1, then the input used to be 0. You can always reconstruct the input from the output. No information lost and no mandatory heat. If you look at a NAND gate, it is irreversible. Inputs such as 0, 0, 0, 1, and 1, 0 all produce output 1. The inputs are gone and those information has been erased. A memory bit holds 0 or 1, two distinct physical states. Resetting it to 0, regardless of what it held, collapses two possibilities into one. That's a reduction in systems entropy. According to the second law of thermodynamics, if we decrease entropy of a system, entropy of the environment must be increased. We have this formula to tell minimum energy required to erase one bit. In here, T is the temperature of the environment. Lower the temperature, lower the flow. Then we have Boltzmann constant. This acts as a bridge between microscopic molecular motion and microscopic heat. Now here's Ln2, the natural log of 2. This encodes the binary operation itself. It represents two states collapsing into one. If we plug the numbers at room temperature, it gives 2.87 zetajoules per bit. That's roughly 0.18 electron volts. This is not an engineering target. This is actually ceiling governed by the laws of physics. Imagine a perfect computer with perfect materials and perfect code. Even if it erases one bit, it must release heat to the universe, no matter what. This is where things get interesting. In December 1867, James Maxwell describes a thought experiment to a letter to a fellow physicist. And the thing is, that thought experiment is actually breaking the second law of thermodynamics. Picture a sealed gas container with a wall, a trapdoor, and a tiny being controlling the door. It sorts fast molecules on one way and slow molecules into the other way. After some time, one side heats up and the other side cools down. A temperature difference built out of nothing. This is Maxwell's demon, and it messed with physicists' head over a century. But in 1982, Charles Bennett found a solution. The thing is, if we look at it, it might seem the measurement itself is costing the energy, but it's not, because there's no law says that measurement costs energy. But a demon with finite memory must eventually erase its records of the sorting. And that eraser is subject to Landauer's bound. Actually, this isn't a philosophical thing or an assumption. We actually proved the whole thing. We proved that Landauer's limit is real and erasure always results in heat. In 2012, physicist Antoine Beirut and his colleagues achieved the first direct laboratory measurement of the Landauer's limit. They took a microscopic silica bead smaller than a human red blood cell and suspended in water inside a double-well optical trap created by two crossed laser beams. The trap creates two stable positions, like a valley with 2 points. When the bead positions to left well, it's 0, and when it positions to right well, it's 1. To erase the bead, the researchers simultaneously lowered the barrier between the two wells. What they found is when they erased the bit, it released heat, proving that every erasure of logic has a thermal cost. Okay, we talked about Landauer's limit, but the thing is, our modern processors are nowhere near it. Even now, a state-of-the-art 5 nanometer CMOS chip is actually 1000 times above the Landauer's flow. But the thing is, we are keep improving and we keep developing more and more efficient computers, be it in the classical side or in the quantum side. So it's safe to assume that in the near future, we might eventually reach that limit. there's another interesting thing. When calculating the Landauer's bound, we assume that everything is happening in an infinitely slow manner. We call it a quasi-static process. But real processes run nanoseconds clock cycles. It's not an infinitely slow process. And according to the thermodynamics, faster erasure always costs more energy. But actually, there is a way to avoid this Landauer's limit. It is by using reversible computing. The idea behind reversible computing is that the logic gates can always be reversed. As an example, we have Toffoli gate and Friedkin gate. But there's a catch. Reversible computing doesn't eliminate Landauer's cost. It just forgets it. It creates garbage bits, intermediate results that would normally be discarded, but they haven't. And those garbage bits have been accumulated in the memory. From all of this, what we can say is no matter how good our computers are and what are the improvements in quantum computers, we will always face that fundamental limit in the universe.